Hello, today we're going to cover basic probability. If you look at the syllabus, you'll see the things we're going to cover. We're going to cover the probability of an event, we're going to cover complementary events, and we're going to cover the expected number of occurrences. Look at the formula booklet, you'll see two of the formulas that we're going to come across in today's lesson. So probability is the chance of an event occurring, and we assign a probability a number between 0 and 1. Probability of 0 would mean the event is impossible, and the probability of 1 meaning the event is certain. If the probability is 0.5, it has an equal chance or an even chance. If the probability is bigger than 0.5, we'd say it's likely or very likely to happen, and if it's less than 0.5, we say it's unlikely or very unlikely to happen. Some of the terms you're going to come across are experiment, which might be rolling a dice over here. Trials would be the number of times that we roll the dice, perform the experiment. An outcome is a particular result, so perhaps getting a 5 on the dice. An event, again, could be a particular outcome, could be getting a 5 on the dice or getting an odd number on the dice, for example. And the sample space, denoted by the letter U, is the set of all possible outcomes. So on the dice, that would be the numbers 1, 2, 3, 4, 5, 6, the numbers on the sides of the dice. And on the coin, the sample space would be heads and tails. The notation for probability of an event is P bracket A. So as you can see, all probabilities, all events, are between 0 and 1. In experimental probability, we might perform an experiment and collect data for the results. Look at the example at the bottom. When this red plastic cone was tossed in the air 279 times, it fell on its side 183 times and fell on its base 96 times, as shown. So the relative frequency of lying on its side would be 183 over 279.656, and the relative frequency of landing on its base would be 96 over 279 or 0.344. And in the absence of any more data, those would be our best estimates of the probability, and we call that the experimental probability. So here we have 80 packets of collectible cards. They've been opened, and 23 of them were found to have contained a special card, a rare card. And the question is, estimate the probability that the next pack of cards opened also contains a special rare card. So we need to calculate the relative frequency. So you can see that the relative frequency is simply 23 out of 80, and that's our best estimate for the probability of getting a rare card. So theoretical probability is when we know that all the outcomes are equally likely. For example, the sides on the die are all equally likely. Then we can calculate probabilities based on the number of outcomes corresponding to a particular event A and the total number of outcomes in the sample space. And again, all the probabilities lie between 0 and 1. So on this standard dice, which was rolled, we're asked to find the probability that the outcome is a prime number. So our first task would be to identify the sample space. As you can see, sample space are the numbers 1, 2, 3, 4, 5, 6. And then we need to know how many of those outcomes are prime numbers. So 2, 3, and 5 are prime numbers. So the number of outcomes in set A is 3. And the number of outcomes in the sample space is 6. As shown, So the probability of rolling a prime number is 3 in 6, or 1/2. The complement of the event, denoted A prime or A dash, is the probability that the event does not happen. And since an event either happens or doesn't happen, the sum of these probabilities, happening and not happening, must add up to 1, as shown here. And we can rearrange that equation to give the probability of an event not happening is 1 minus the probability of the event happening. A dash is called the complement of event A. So here we're asked to determine the chance of getting in 6 and not getting a 6. If we first identify the sample space again are the numbers 1, 2, 3, 4, 5, 6. So the probability of getting a 6 is 1 in 6. To calculate the probability of not getting a 6, we can identify all the outcomes that are not a 6, 1, 2, 3, 4, or 5. So the probability of not getting 6 would be 5, 6. Alternatively, we can subtract the probability of getting a 6 away from one whole. So the probability of not getting a 6, again, is 5, 6. In this example, the probability of no buses arriving in a 10-minute interval is 0.4. We're asked to calculate the probability of at least one bus arriving in the 10-minute interval. So again, these events are complementary. Either a bus doesn't arrive in that 10-minute interval, or at least one bus will arrive in that 10-minute interval. So the probability of at least one bus arriving is 1 minus 0.4, which is equal to 0.6. And finally, the expected number of occurrences. If we know the probability of an event happening, and we repeat that experiment several times, we can estimate the expected number of occurrences of that event by multiplying the probability by the number of trials. Okay, and the answer doesn't have to be a whole number, okay, although we could round it to a nearest whole number if that's more appropriate. So here we have an example where the probability of hitting the bullseye is 0.3. If the archer takes 12 shots, find the expected number of bullseyes. So we can just use the calculation that the expected number is equal to the probability times the number of trials. The expected number in this case is 3.6. In this last example, we're told the probability or the percentage of shots that Michael Jordan made in his career was 83.53. Okay, so from that we can write down a probability. And it says if he played one more game and had 18 more shots from the free throw line, how many shots would we expect him to have made? So again, using the same calculation, multiplying the probability by the number of trials. And that means multiplying 0.8353 by 18, giving us approximately 15 shots.